hope is not a strategy. That's quite a statement, isn't
Yeah.
it? Especially when you're talking about large-scale computing.
It really cuts to the chase.
Yeah, it asks that fundamental question.
Yeah.
How do you actually run these incredibly complex systems effectively, particularly, at massive scale?
It's a huge challenge.
So today, we're doing a deep dive into some really foundational material. We're looking at excerpts from the book, Site Reliability Engineering, how Google runs production systems.
A seminal work in the field.
Definitely. Our mission here is to pull out the most important insights about SRE, where it came from, how it works, and how it really shifted the way we think about managing technology.
Exactly. We're not just looking at what SRE is, but digging into the why. Why did Google go down this path? How does it challenge those traditional operational ideas?
And what does it tell us about building systems that are genuinely robust?
Right. Systems that can actually handle the scale and complexity we see today.
And we've tailored this deep dive for you, the listener. We want to make sure you come away with those key insights, maybe some aha moments, and feel really well informed on this crucial topic.
Yeah, hopefully demystify it a bit.
Okay, let's unpack this. Where should we start? Maybe with the old way.
Makes sense. The historical context is important.
So let's think back to the traditional approach to managing services, what people often call the sysadmin model.
Right. So traditionally, companies would, assemble various software components, often off-the-shelf stuff, deploy them.
And then hand them over to a team of system administrators, the sysadmins, to actually run them day to day.
Exactly. It was very much about reacting, keeping the lights on, handling updates, fixing things when they broke.
A very common way of operating, especially back then.
Oh, absolutely. And, it had its advantages, especially initially.
Like what?
Well, it was relatively easy to get started, right? You didn't need a super specialized skill set for basic administration. There was a decent talent pool.
Yeah.
And lots of existing tools or software components you could use. You weren't reinventing the wheel.
So lower barrier to entry, maybe?
Yeah, pretty much. Easy to get off the ground.
And here's where it gets interesting. That sysadmin model, especially the split it created between development and operations, dev and ops, it had some pretty significant downsides.
Oh, definitely.
Yeah.
Both direct and indirect costs.
Let's talk direct costs first.
Yeah.
The big one seems to be scaling, right? If you're running a service with lots of manual intervention.
It gets expensive fast. As the service grows or the traffic grows, you basically need more people.
Your sysadmin team has to scale up pretty much linearly with the service side.
Exactly. More users, more servers, more sysadmins. Not very efficient.
And that's just the obvious cost. What about the indirect ones?
Yeah. These are often trickier, but arguably more damaging in the long run. They really stem from that fundamental split, that friction between the dev team and the ops team.
Different tribes, almost.
Kind of. They often had different backgrounds, totally different skill sets, different incentives even. They spoke different languages, technically speaking.
Different priorities, too, I imagine.
Absolutely. Different assumptions about risk, different ideas about how stable the product needed to be. It just creates this natural tension.
So this often boiled down to a clash over speed, right? How quickly new stuff could be released.
Precisely. Developers, naturally, they want to build cool new features and get them out to users fast. That's their driver.
Say they're working the wild.
Yeah. But the ops team, their main concern is stability. They're the ones holding the pager at 3 a.m. They want to make sure the service doesn't break.
And since most outages are caused by some kind of change, a new release, a config update,
those two goals are often fundamentally at odds, speed versus stability.
the book calls it trench warfare, which paints quite a picture.
It really could feel like that. Ops teams would try to protect the system by putting up gates, launch gates, change gates.
What did those look like in practice?
Well, imagine a pre-launch review checklist that includes checking for every single problem that had ever caused an outage before. That list just grows and grows.
Yeah, bureaucratic nightmare.
Totally. And then the dev teams, they'd learn how to game the system.
How so?
They'd try to avoid formal launches. They'd do more flag flips, turning features on quietly, or incremental updates, tiny changes hoping to fly under the radar.
Or even breaking up the product, sharding it, so each piece seemed less risky to review.
Exactly. It just becomes this adversarial dance, trying to work around each other instead of working together.
Okay, so that's the problem space. A pretty dysfunctional relationship, it sounds like. Given that constant battle, how did Google approach this? Did they just try to manage the conflict better?
No, that's the key thing. They didn't just try to manage it. They fundamentally rejected the premise that this conflict was inevitable.
Uh,
Their solution was radically different. Site reliability engineering, SRE.
and what was the core idea?
Instead of hiring traditional sysadmins, they decided to hire software engineers to run their production services.
Okay.
And crucially, they tasked these engineers not just with running things, but with building systems to automate the manual work sysadmins traditionally did.
So automate the toil away.
Precisely. There's a great quote in the source. SRE is what happens when you ask a software engineer to design an operations team.
I like that. Very direct.
It really captures the essence. This whole approach originated with Benjamin Traynor Sloss at Google. He was a software engineer,
Right.
and he basically designed the production team, as it was first called, the way he would want it to operate if he were on that team, applying engineering thinking to operations.
And that evolved into the SRE teams they have today. What does that team composition actually look like? Is it just standard software engineers?
It's an interesting mix, actually. About 50 to 60% are Google software engineers, the standard SWEs hired through their main pipeline. But the other 40 to 50% are candidates who are almost SWEs, maybe 85, 99% of the qualifications. But they bring these other, often rare, super valuable technical skills.
Like what kind of skills?
Deep knowledge of UNIX system internals, for example, or serious networking expertise down to layers 1, 2, and 3, skills that aren't always common even among great software developers.
Got it. So it's a blend.
It's a blend. But the key thing, the common thread across all SREs is this shared belief in and aptitude for building software systems to solve complex problems.
Not just fixing things, but engineering solutions.
Exactly. And that diversity of background, that mix of SWEs and these other specialists often leads to really clever, really high quality systems because they're bringing different perspectives together.
That makes sense.
And there's a core principle baked into the SRE role itself. The book says SREs will quickly become bored by performing tasks by hand.
Huh. I can relate to that.
Right. They have that inherent drive and, critically, the skill set necessary to write software to replace their previously manual work, even if it's complex automation.
So the predisposition to automate is built in. It's not just encouraged, it's expected.
It's fundamental. And to make sure it actually happens, to prevent SREs from just getting swamped with operational tasks, Google implemented a crucial rule,
Which is?
the 50% cap on the aggregate ops work for SRE teams.
Okay, explain that. What counts as ops work?
Things like handling tickets, on-call duties, manual interventions, the reactive stuff. The rule is that, averaged across the team, this kind of work shouldn't take up more than 50% of their time.
And the other 50%?
That's reserved for engineering, building automation, improving monitoring, developing new tools, performance tuning, proactive, long-term improvement work.
What happens if a team consistently goes over that 50% ops cap? If they're just constantly fighting fires?
This is where it gets really clever.
Oh.
If an SRE team is overloaded with ops work for too long, the extra operational burden is deliberately shifted back to the product development team.
Oh, wow. Really?
Yes, the developers who wrote the software literally have to take on some of the operational load, maybe even take pager duty.
That sounds potentially painful for the developers.
It can be, but it creates this incredibly powerful feedback loop. Developers are now directly incentivized to build systems that are more reliable, more automated, easier to operate.
Because otherwise they'll be the ones dealing with the consequences.
Exactly. It aligns incentives beautifully. The ultimate goal shifts from just automated systems, scripts doing tasks, to truly automatic systems. Self-healing, self-managing.
That's a profound difference.
Yeah.
So looking back at this SRE model, what are the big advantages compared to the old sysadmin way?
They're pretty significant. You get much faster innovation because you're not stuck in that DevOps trench warfare.
Yeah.
There's a higher acceptance of change because it's managed via things like error budgets, which we'll get to.
Okay.
It's also way more cost-effective. SRE teams scale sublinearly with the service size, unlike the linear scaling of sysadmins, because automation handles the growth.
Right. You don't need proportionally more people.
Precisely. It bypasses that core DevOps dysfunction. And interestingly, it even helps improve the skills of the product developers through that potential cross-training and feedback loop. They learn more about building robust distributed systems.
Makes transfers between teams easier too, I bet. Spreads the knowledge.
Definitely. But it's not all sunshine and roses, right? There must be challenges.
Oh, absolutely. It's not a magic bullet. The biggest challenge is probably hiring.
The high bar for SREs.
Exactly. Finding people with that specific blend of software engineering and systems expertise is tough. The talent pool is just smaller.
Makes sense.
And the other thing is SRE teams often have these unorthodox approaches, as the book puts it. Things like managing error budgets strictly.
Yeah. Not always immediately popular with dev teams, maybe.
Can be. So you need really strong management support to back the SREs and ensure their principles are actually followed, even when it causes some initial friction.
Right, it requires organizational buy-in.
One quick point, people often ask how SRE relates to DevOps. How does the book position that?
Yeah. It's an interesting relationship. You can kind of see DevOps as a broader philosophy, a generalization of some core SRE principles that can apply more widely.
Okay.
Or you could flip it and say SRE is like a very specific, opinionated, and highly successful implementation of DevOps principles with its own unique additions and rigor.
So related but distinct.
Yeah, cousins maybe, not identical twins.
All right, let's shift gears a bit and talk about the core tenets. What are the day-to-day principles that guide SRE teams?
Sure. SREs have broad responsibilities. We're talking availability, latency, performance, efficiency, change management, monitoring, emergency response, capacity planning. It's a wide mandate.
Covering the whole life cycle, really.
Pretty much. But within that, there are some really key tenets that define the SRE mindset. Some are quite counterintuitive at first glance.
Oh, like what? Give me an example.
Okay, how about blameless postmortems?
I've heard of this. The idea is no finger pointing after something goes wrong.
Exactly. Google has a strong culture of writing detailed postmortems for all significant incidents, even minor ones that didn't page anyone. But the absolute key is that they are rigorously blame-free.
Why is that so important?
Because the goal isn't to find who messed up. It's to understand what went wrong in the system. The processes, the technology, the assumptions. The aim is to expose faults and apply engineering to fix these faults systemically.
So focusing on process improvement, not individual punishment.
Precisely. If people fear being blamed, they won't be open about mistakes, and you'll never find the real root causes. Blamelessness encourages learning.
That makes a lot of sense culturally. What's another big tenet? You mentioned error budgets earlier.
Yes, the error budget. This one is truly profound, maybe the cornerstone of SRE.
Okay, lay it on me.
The core revolutionary idea here is that 100% is the wrong reliability target for basically everything.
Wait, 100% reliability is wrong. That sounds wrong.
I know, it feels counterintuitive. Obviously, there are exceptions like, medical devices, pacemakers.
Sure, critical systems.
But for most services, aiming for 100% uptime is not only practically impossible, it's often not even beneficial to the user.
How so? Why wouldn't a user want 100% uptime?
Think about the entire chain connecting a user to your service. Their laptop, their home Wi-Fi, their internet service provider, the power grid.
Right. Lots of potential points of failure outside the service itself.
Exactly. The aggregate availability of all those other systems is way, way less than 100%. Probably not even 99.99% most of the time.
So even if my service is 100% perfect, the user might not be able to reach it anyway.
Precisely. That last tiny fraction of availability you might spend enormous effort and money achieving, say, going from 99.999% to 100% gets completely lost in the noise of the rest of the internet. The user literally cannot perceive the difference.
Okay, I see the point. So if 100% is the wrong target, what is the right target?
And this is fascinating. The book argues it's fundamentally a product question, not just a technical one. Meaning, you have to decide, based on business needs, what level of availability will actually keep users happy. Consider their expectations, what alternatives they have, how they use the service. Maybe 99.9% is perfectly fine. Maybe for a critical financial system, it needs to be 99.99%.
So the business defines the target service level objective, or SLO.
Exactly. And once you have that target SLO, say 99.99% availability, the error budget is simply what's left over.
1 minus the target.
Up 100% minus 99.99% is 0.99% per hour of allowable downtime or unavailability or errors. That's your budget.
Okay, so you have a budget for errors.
Yeah.
What do you do with it?
You spend it. This is the genius part. That budget represents the acceptable level of risk the business is willing to tolerate. SREs and developers can spend that budget by taking calculated risks.
Like launching new features faster.
Exactly. Pushing updates more frequently, experimenting. As long as you stay within the budget over the measurement period, like a month or a quarter, you're good. If you burn through your budget too quickly.
And then you have to slow down, put the brakes on releases.
Precisely. Maybe freeze launches until the service recovers its reliability and earns back some budget.
Wow. So it directly connects reliability to release velocity.
It completely reframes the whole conversation. It resolves that fundamental conflict between dev and SRE we talked about earlier.
So,
Because the goal is no longer this abstract, impossible zero outages. Instead, both teams, dev and SRE, share the goal of spending the error budget efficiently to maximize future velocity while staying within the SLO.
so outages aren't inherently bad anymore.
They're an expected, measured, and managed part of the process of innovation. It makes reliability a concrete resource that everyone manages collaboratively rather than something ops just defends.
That is, yeah, that's a really powerful concept. Okay, what else? Monitoring must be key.
Absolutely crucial.
Yeah.
But Google's philosophy on monitoring is also quite specific.
Wow.
The main principle: monitoring should never require a human to interpret raw data to decide if there's a problem that needs action right now. The software should make that decision.
So no dashboards full of squiggly lines that someone has to stare at constantly.
Ideally, no. Humans are slow and unreliable at that. They define 3 valid kinds of output from a monitoring system.
Okay, what do I?
First, alerts. This means wake someone up, human action needed immediately, should be urgent, actionable, and about real problems impacting users or the service.
Got it. PagerDuty stuff.
Yep. Second, tickets. This means human action is needed, but not right now, maybe within a few hours or days. It goes into a tracking system. Think non-critical capacity issues, upcoming certificate expirations, that sort of thing.
Okay, needs attention, but not panic.
Right. And third, logging. This is just recording events for later diagnostic or forensic use. Nobody reads logs unless an alert or a ticket prompts them to investigate something specific.
So alerts for emergencies, tickets for tasks, logs for deep dives, very clear distinctions.
Keeps the noise level down and focuses human attention where it's truly needed.
And when those alerts do fire, triggering emergency.
That's where emergency response comes in. The key metric they focus on here is MTTR, mean time to repair. How quickly can you fix the problem?
Makes sense. Faster fixes mean less downtime.
Exactly. And they have this interesting observation. Humans add latency.
Meaning, getting a person involved slows things down.
Often, yes. Even if a fully automated system fails slightly more often, if it can recover automatically without human intervention, it might actually have higher overall availability than a system that fails less but requires slow human response each time.
So automation is key even in recovery. But sometimes humans are needed, right?
Absolutely. And when they are, preparation is critical. Thinking through potential failure scenarios ahead of time and documenting the steps to diagnose and fix them in a playbook.
Like a checklist for emergencies.
Kinda, yeah. They found that having a well-practiced playbook provides roughly a 3x improvement in MTTR compared to just winging it when the pressure's on.
3 times faster. That's huge.
Massive. They even run drills like the Wheel of Misfortune, where they simulate outages to practice these playbooks and identify gaps.
Proactive practice for reactive situations.
Yeah.
Okay, another big one seems to be managing change itself.
Huge. The source states that around 70% of outages in complex systems are due to some kind of change being pushed. Live code updates, configuration changes, data pushes.
Wow, 70%. That's the vast majority.
It really highlights why change management is so critical. SRE best practices lean heavily on automation here.
How does automation help manage change risk?
3 main ways. First, doing progressive rollouts. Don't push the change to everyone at once. Start with a tiny fraction of users or servers, then gradually increase if things look okay.
Canary releases, that kind of thing.
Exactly. Second, having quick and accurate detection of problems. Your monitoring needs to spot issues caused by the change almost immediately.
So you know if the canary is sick.
Right. And third, having the ability to perform safe, fast rollbacks. If you detect a problem, you need to be able to revert the change automatically and quickly to minimize the impact.
So roll out slowly, watch carefully, roll back fast if needed.
You got it. Automation removes the slow, error-prone human element from this loop, which paradoxically allows you to increase both the velocity of releases and the safety of the system simultaneously.
Faster and safer.
Nice.
What about looking ahead, capacity planning?
Yeah, that's core SRE responsibility too. Demand forecasting and capacity planning. Basically, making sure you have enough resources, servers, network bandwidth, storage, not just for today, but for projected future growth.
So the service doesn't fall over when it gets popular.
Right. SREs are typically in charge of ensuring that capacity is provisioned ahead of demand. And related to that is efficiency and performance.
Making the most of the resources you have.
Exactly. SREs are constantly looking at resource utilization, CPU, RAM, disk, and finding ways to make software more efficient, tune performance, reduce latency. Doing more with less saves money and effectively adds capacity.
Okay, that gives a great overview of the SRE principles. Now, maybe we could peek behind the curtain a bit. What kind of infrastructure makes all this possible at Google?
Yeah, understanding the environment helps contextualize SRE. Google's infrastructure is, well, unique. They run custom-designed data centers.
Not just renting space somewhere.
No. Purpose-built facilities filled with their own proprietary hardware. And it's mostly homogeneous, meaning lots of identical or very similar machines, which simplifies management massively.
Okay. And they have specific terminology too, right? Machine versus server.
Yes, that's an important distinction they make. And machine is a physical piece of hardware, or maybe a virtual machine, but a server is a piece of software implementing a specific service, like the Shakespeare backend we might discuss later.
And any machine can potentially run any server.
Generally, yes. Resources are allocated dynamically by their cluster management system called Borg. A server isn't tied to specific hardware.
Got it. Can you give us a sense of the scale, like the physical layout?
Sure. The book describes it like this. You have tens of machines placed in a rack. Then racks stand in a row, and one or more rows form a cluster.
Okay, building blocks.
Right. Then usually a data center building houses multiple clusters. And finally, multiple data center buildings that are located close together form a campus. It's layers upon layers of scale.
Mind-boggling, really. And the networking connecting all this must be pretty advanced.
Oh, incredibly. Inside the data center, they developed this thing called Jupyter, which is essentially a massive, super fast virtual switch.
How fast are we talking?
It's built using a Clos network fabric, a special design for high bandwidth and redundancy. In its largest versions, it offers something like 1.3 petabits per second of bisection bandwidth. Just astronomical speed for moving data within the data center.
Wow, and connecting the data centers globally.
That's their backbone network, called B4. It's a software-defined network, an SDN, built using OpenFlow.
SDN, meaning they control the network routing using software.
Exactly. They can programmatically manage global traffic flows, optimize routes, react to failures, treat the entire global network almost like a distributed software system, gives them incredible control and efficiency.
Okay, so custom hardware, massive scale, cutting-edge networking. What software orchestrates all this? You mentioned Borg.
Right, Borg is key. It's Google's internal cluster operating system. Think of it as similar in concept to Kubernetes or Apache Mesos, but developed much earlier and tailored specifically for Google's needs.
What does it actually do?
It manages jobs and tasks across the machines in a cluster. When you want to run a server program, you submit a job to Borg. Borg finds available resources on machines, starts their tasks, monitors them.
And handles failures.
Crucially, yes. If a task crashes or a machine dies, Borg automatically detects it, kills the malfunctioning task if necessary, and restarts it, potentially on a completely different machine in the cluster. It provides that vital self-healing capability.
So applications don't need to worry so much about individual machine failures.
Largely no. But since tasks can move around between machines, their IP addresses change constantly.
Ah, so how do services find each other?
That's where BNS, the Borg naming service, comes in. It's a critical layer of indirection. Instead of using fragile IP addresses, services refer to each other using a stable BNS name and index number, like Shakespeare backend point 3.
And BNS translates that name into the current IP in port.
Exactly. It's like DNS, but specifically for services running inside Borg clusters. Absolutely essential.
Makes sense. What about storage? Where does all the data live?
Multiple layers there, too. At the base, there's D, which is described as a distributed file server running on almost every machine, optimized for high throughput. Built on top of that is Colossus, which is the successor to the original Google File System, GFS. It's a massive, cluster-wide, distributed file system.
So like a giant hard drive spanning thousands of machines.
Kind of, yeah. And then, built on top of Colossus, you have Google's database-like services. The two big ones mentioned are Bigtable.
They're NoSQL database, right?
Yep. Famous key value store, massively scalable, and Spanner.
Spanner's the globally consistent SQL-like one. That sounds incredibly complex.
It is. Providing ACID transactions with external consistency across global data centers was a huge engineering feat.
Okay, so Borg manages compute, BNS handles naming, Colossus Bigtable Spanner handles storage. How do users actually get routed to the right data center in the first place?
That's the job of GSLB, the Global Software Load Balancer.
What does it do?
When your browser looks up, say, google.com, GSLB gets involved. It considers your location, the current load on different data centers, their health status, and directs your DNS query to the IP address of a Google front-end server in the best data center for you at that moment.
So it load balances globally at the DNS level.
Yes, and also at other levels, like directing RPCs between services internally. It's all about minimizing latency and ensuring capacity is available.
Any other key system software components we should mention?
Well, there's Chubby, which is a distributed lock service. Sounds simple, but it's crucial for coordinating activities between distributed processes, like ensuring only one process is the master for a service, or holding distributed locks for consistency. It provides a simple file-like API.
Okay, for coordination and monitoring.
That's Borgmon. It's the system that periodically scrapes metrics, like request counts, latency, error rates, from all the running servers. This data feeds dashboards, triggers alerts via Borg, and provides the historical data needed for analysis and planning.
Got it. So that's the system software. What about the software development infrastructure itself? How do they build the services that run on all this?
It's also quite distinctive. Google famously uses a heavily multi-threaded programming model to maximize efficiency on their hardware.
Taking advantage of multi-core processors.
Right. And for communication between services, they rely heavily on RPC's remote procedure calls using their internal Stubby framework.
Is that related to gRPC?
Exactly. gRPC is the open source version of Stubby. It allows services to call methods on other services across the network as if they were local function calls.
And how do they structure the data for these calls?
They use protocol buffers, or protobufs. It's Google's language-neutral, platform-neutral mechanism for serializing structured data. Think of it like XML or JSON, but much faster, smaller, and with stricter schemas, highly efficient for RPCs.
Okay, and the development process itself. How do engineers actually write and release code?
One huge thing is their monorepo. Almost all of Google's code lives in a single, shared version control repository.
Everything. Wow.
Pretty much. This means an engineer working on one project can easily find, read, and even propose changes to code in a completely different project if they find a bug or dependency issue.
Encourages collaboration and code sharing?
Definitely. They also have massive distributed build systems for parallel compilation, so building large projects is fast, and a huge emphasis on automated testing.
Continuous integration.
Absolutely. Every proposed change, a change list or CL, goes through automated tests before it's submitted. And many projects use push-on-green systems where once a CL passes all tests, it can be automatically deployed to production relatively quickly.
Very fast. Automated release cycle then.
Enabled by all the infrastructure and SRE practices we've been talking about.
Okay, that's a lot of infrastructure and process. Let's try to tie it together with that hypothetical Shakespeare service example from the book. It helps make it concrete.
Good idea. So the premise is a simple service. Search all of Shakespeare's works for a specific word.
Right, and it has two main parts.
Yeah. There's a batch component, maybe a MapReduce job that runs once or very infrequently. It reads all the text, builds a search index, and stores that index in, say, Bigtable.
So pre-processing the data.
Exactly. And then there's the application front end, the user-facing part, which needs to be running continuously to handle search requests from users.
Okay, so let's walk through the life of a request step by step. I, the user, type shakespeare.google.com into my browser and search for, say, Forswear. What happens first?
Okay, first step. Your browser needs the IP address for shakespeare.google.com. It sends a DNS query. This eventually reaches Google's DNS servers, which consult GSLB.
And GSLB picks the best data center and front-end server IP based on load and location.
Correct. GSLB returns that specific IP address back to your browser.
Got it. Now my browser has an IP. What next?
Your browser opens a TCP connection to that IP address. The machine listening there is a Google Front-End, or GFE. It's basically a smart reverse proxy.
What does the GFE do?
It terminates the connection, maybe handles SSL, and figures out which internal service the request is for, in this case, the Shakespeare service.
Okay, so the GFE knows I want Shakespeare. Then what?
The GFE needs to find a running instance of the Shakespeare front-end server program, so it contacts GSLB again, but this time for internal load balancing. GSLB picks an available Shakespeare front-end instance.
Running somewhere in that data center.
Exactly. And the GFE sends an RPC, maybe using Stubby and protobufs containing your search query, Forswear, to that specific front-end instance.
Phew! Okay, The request finally reached the actual Shakespeare application front end. What does it do?
The front end's job is mainly coordination. It knows it needs the actual search results from a back-end server. So it contacts GSLB again to find the BNS address, that service.instance name, of a suitable Shakespeare back-end task.
So another layer of load balancing.
Yep. Once it has the BNS address, the front end sends another RPC, again with the query, to that chosen back-end instance.
Right, now we're at the back end. This must be where the real work happens.
Correct. The back-end task receives the request, knows it needs to look up Foursquare in the index, which lives in Bigtable. So it contacts the appropriate Bigtable server, or servers, which finds the relevant entries in the index. Right. Bigtable returns the results, example, which plays and lines contain Foursquare, back to the Shakespeare backend task.
And then the answer flows back up the chain.
Exactly. The backend sends the results back to the front end via RPC. The front end formats the response and sends it back to the GFE. The GFE sends it back over the internet to your browser.
And my browser displays the results.
Wow. And the truly amazing thing, as the book points out, is that this whole multi-stage, cross-machine, potentially cross-data center journey happens in maybe just a few hundred milliseconds.
Despite all those potential points of failure along the way.
It really speaks to the robustness built into each layer, the rigorous testing and careful rollout, the automatic failure recovery via Borg, the load balancing, everything we've discussed.
It's why, as they say, people sometimes use Google search to check if their own internet is working.
Yeah.
It's just assumed to be up.
That's the level of reliability SRE aims for. Now, there are also interesting decisions about how you organize the jobs and data for a service like this.
Like redundancy. How many copies of the backend do you run?
Right. Let's say load testing shows you need, at peak, maybe 35 backend tasks to handle the query load. You wouldn't just run 35.
Why not?
You'd use n plus something redundancy. The book suggests n plus 2 as common, so you'd run 37 tasks.
Why n plus 2? What does the first two cover?
One extra task covers capacity loss during a rolling update, where you take tasks down one by one to update them. The second extra task covers the possibility of an unrelated machine failure during that rolling update.
Ah, planning for concurrent issues. Very careful.
It's about maintaining capacity even during routine operations and unexpected failures. They'd also distribute these backends globally, maybe clusters in the US, Europe, Asia.
They'd be close to users everywhere.
Exactly. But maybe, the book suggests, in a region with lower traffic like South America, they might choose to run only n+1 redundancy.
Cutting it a bit closer. Why?
To save maybe 20% on hardware costs in that region, it's a calculated risk. They accept that during an n+1
Welcome to the deep dive. We dig into sources to pull out the key insights for you. Today, we're looking at how Google, one of the biggest tech players out there, manages its systems. The scale is just immense. Our main source is the book Site Reliability Engineering, How Google Runs Production Systems. It's pretty foundational, and we're going to focus on 3 core ideas from it. How they embrace risk, how they use service-level objectives, or SLOs, and how they work to eliminate something called toil. Basically, this is your shortcut to understanding what makes Google's approach to running things different and pretty effective, it seems.
Yeah, and it's fascinating because some of these ideas really push back against how people usually think about operations. Like, you'd expect Google to shoot for 100% reliability, right? Perfect uptime.
Absolutely.
But that's actually not the goal, which is, surprising.
Okay, let's definitely unpack that. It sounds, totally counterintuitive. Why would Google choose not to build perfect systems?
Well, it sounds weird, but there's solid reasoning behind it. Getting that last bit of stability, it costs a lot. And that's in, 2 ways. First, the obvious one. More machines, more redundancy. Just raw costs.
Right, the hardware.
But then there's what they call opportunity cost. That's maybe even bigger. It's all the engineering time spent chasing near-perfect uptime.
Instead of building new things.
Exactly. Instead of building features users actually see and care about.
Yeah.
The book even mentions that getting 1 extra 9 of reliability can cost 100 times more than the previous improvement.
Wow, 100 times. So it's diminishing returns big time. You're spending huge effort for something maybe no one notices.
Precisely. And that ties into the user experience bit. Most users, honestly, they can't tell the difference between, say, 99.99% reliable and 99.999% reliable.
Why not?
Because their own connection, their phone, their Wi-Fi, that stuff is usually less reliable anyway. It dominates their experience. Like the quote says, someone on a 99% reliable phone won't notice if your service is 4 nines or 5 nines reliable.
That's a really good point. We focus on our server, but the user's reality is much broader. So the goal isn't perfection. It's
Oh,
optimizing overall user happiness, which includes features and performance, not just uptime.
you got it. It's about balancing that risk of something breaking with the speed of innovation and just running things efficiently. Google thinks about risk as like a spectrum. They want services to be reliable enough, but no more reliable than needed.
Reliable enough.
Yeah, and that target, that availability goal. It's a minimum, sure, but it's also kind of a maximum.
How's at a maximum?
Because if you're always way more reliable than your target, means you probably could have taken more risks, launched features faster, maybe saved some money, cleaned up tech debt.
Okay. So overachieving reliability mean you missed opportunities elsewhere.
Exactly. It allows for deliberate, thoughtful risk-taking.
Okay, that reframes it completely. But if perfect isn't the goal, how do they figure out what enough actually looks like? How do you quantify acceptable downtime?
Right. Well, first, for these big global services, they don't really use simple uptime percentages based on time.
Why not?
Because a service might be down in one place but working fine elsewhere, so is it up or down? That's kind of meaningless globally.
True.
So instead, they focus on request success rate. Basically, successful requests divided by total requests.
Over a certain period.
Yeah, usually over a rolling window. So the example they give is if you serve 2.5 million requests a day and your target is 99.99%,
4 nines.
right, you can actually have up to 250 errors that day and still meet your target. It makes a goal concrete, and you can apply this to non-serving stuff too, like batch jobs success might be records processed correctly.
That makes way more sense for distributed systems. But different services must have wildly different ideas of enough, like Google search versus, I don't know, an internal tool.
Oh, absolutely. They look at a whole bunch of factors. For consumer stuff like search, maps, Gmail, YouTube, they consider what users expect, obviously. Is there direct money involved? Is it free or paid? What are competitors doing? Is it for regular consumers or enterprise customers?
Okay.
So Google Workspace, for businesses, that has super high targets, internally and externally. There are often penalties if they miss them.
Makes sense. Businesses rely on it.
But then you take YouTube, especially back when Google first got it, it had a lower target. Why? Because they were focused on just pumping out features, growing like crazy. Reliability was important, but speed was more important then.
So the target can actually change based on the product's strategy or life cycle stage.
Exactly. It's not just technical, it's deeply tied to the business.
Fascinating.
They also think about different kinds of failure, like profile pictures not loading for a bit. Annoying, maybe, but not critical. But leaking private data, that's a whole different level. That might mean shutting the whole thing down immediately. And planned maintenance, that's different too. That's planned downtime, not counted against the unplanned budget.
Okay.
And cost, of course, is huge, especially for things like ads. They can often directly link request failures to lost revenue. So they actually do the math. Okay, if we made this system 1.9 more reliable, how much more money would we make? Does that extra cash justify the huge cost of getting that extra 9?
Wow, they actually calculate that.
Yeah. And they even look at things like, the typical error rate of home internet connections, which is maybe 0.01% to 1%. That provides a sort of reality check. Making your service vastly more reliable than the network users connect with might be pointless.
That's a great sanity check.
Mm.
What about things beyond just working or not working? Like speed, latency.
Yeah, latency is a big one too. Take AdWords, the ads next to search results. Those cannot slow down search. So super strict latency goals.
Right, search has to be fast.
But AdSense, the ads on other websites, the goal is looser. It just needs to not significantly slow down the page loading.
So it can be a bit slower.
A bit, yeah. And because of that looser requirement, they can optimize how they serve those ads, maybe use fewer locations, save a lot of money. It's an intentional trade-off based on the context.
Clever. But what about infrastructure? Like something internal, like Bigtable, that lots of other Google services rely on. They must have different needs.
That's a classic infrastructure problem.
Yeah.
You've got one service, but many clients. Bigtable is a great example. Some users need it super fast, low latency for user-facing stuff.
Like serving data for maps or something?
Could be. But other teams use Bigtable for huge offline data analysis. They care more about throughput, getting lots of data through, not so much about instant responses. And as the book says, what looks like success for the low latency user might look like failure for the high throughput user.
So how do they handle that? One size
Yeah.
can't fit all.
They don't try to. They partition the infrastructure. They build specific clusters for low latency needs. These have lots of spare capacity, tons of redundancy. They're more expensive. And then they have separate clusters optimized for throughput. These run hotter, less redundancy, but they cost way less, maybe only 10% to 50% of the cost of the low latency one.
So they offer different service tiers, essentially.
Basically, yeah. It makes the cost difference explicit, and it pushes the client teams to really think about what they actually need and choose the right cost-appropriate level.
Okay, this reliable enough idea is complex but powerful.
Right.
It sounds like you need a really clear system to manage it day to day, which brings us to error budgets.
Exactly. Error budgets are key. But first, we need to nail down some terms SRE uses very precisely.
Okay, terminology time.
Right. First is SLI, service level indicator. That's the actual measurement, like request latency or error rate or system throughput, a specific quantitative metric.
Got it, the measurement.
Then SLO, service level objective. That's the target value for your SLI. So average latency should be under 100 milliseconds. That's an SLO.
Target for the measurement.
Okay. And finally, SLA, service level agreement. This is the contract, often with users, that spells out consequences if the SLOs aren't met, usually financial penalties, credits, that sort of thing.
Right, the thing with teeth.
Exactly. And the key point here is, most people, when they casually say SLA, they actually mean SLO, the target itself. SRE's job is mostly about defining good SLIs and meeting the SLOs to avoid ever triggering those SLA penalties.
Why the big fuss about the specific terms? Lots of places just lump it all under SLA.
Because being precise helps everyone understand what's going on. It clarifies what to do if things go wrong. It gives the SRE team confidence, are we healthy or not? And it helps manage user expectations. If users know the SLO, they're less likely to complain if performance is, within the target, even if it's not perfect. It avoids arguments based on feelings rather than data.
Okay, that makes sense. Clarity is key. So,
Yeah.
how do they pick the right things to measure, the SLIs, and set good targets, the SLOs? Can't just be whatever is easy to track from the server.
No, definitely not. Rule number 1 is focus on what your users care about, not just what you can measure easily. You might have to approximate user happiness, but that's the goal. Measuring server CPU when users care about page load time isn't very helpful.
Right. Focus on user experience.
Yeah. And systems generally fall into buckets. User-facing systems, availability, latency, throughput are key. Storage systems, latency, availability, and durability, not losing data. Big data processing, throughput, end-to-end latency. And pretty much all systems care about correctness, doing the right thing. Sometimes you even need to measure things on the client side, like in the user's browser. Because server metrics might look fine, but JavaScript errors could be killing the experience.
Good point. What about how they aggregate the data? Just average latency.
No, averages can be really misleading. You might have 99% of requests be super fast, but 1% are incredibly slow. The average looks okay, but those slow requests ruin the experience for some users.
A long tail problem.
Exactly. So they rely heavily on percentiles, like the 99th percentile latency or the 99.9th. This shows you the worst case experience for most users, not just the average. People generally prefer consistently okay speed over wildly variable speed.
That makes intuitive sense. So when they define an SLO in practice,
They're very specific. Like 99% of GetRPC calls will complete in less than 100 milliseconds measured at the server over a rolling 5-minute window. Really precise. And you might have multiple SLOs for different aspects or different user groups. Choosing the target value itself isn't purely technical either. It involves product managers, business goals. The advice is, don't just base it on what you achieve now. Keep it simple. Never aim for 100%. Have as few SLOs as you really need, and be willing to revisit and adjust them over time.
okay, that's a solid framework. So how does this SLS structure connect back to daily work and innovation? That's where the error budget comes in.
Yes, precisely. The error budget is the mechanism that makes this all work in practice. It's designed to resolve that natural tension, Product dev wants to go fast, push features. SRE wants stability.
A classic conflict.
Right. The error budget gives them an objective, data-driven way to manage it. Product management sets the SLO, say, 99.999% success rate for queries this quarter.
5 nines. Okay.
The monitoring system just measures reality. What's the actual success rate? The difference between the target SLO and reality, that's your error budget.
So if the target is 99.9999%, the allowable error rate is 0.0001%. That's the budget.
Exactly. It's the budget for unreliability. As long as you have budget left, development can push new releases, make changes.
But if something goes wrong, a bad release, a network outage.
It consumes the budget,
Yeah.
uses it up. And if the budget runs out for the quarter, freeze new launches until you earn more budget back or the quarter resets.
Wow, so it forces a conversation.
Totally. It aligns incentives. Development doesn't want launches frozen, so they become invested in reliability too. They start pushing for better testing, maybe slower rollouts when the budget gets low. They become kind of self-policing. And it works the other way too. If a team finds it almost impossible to spend their error budget because the SLO is too tight, they might actually argue to loosen the SLO.
Loosen it to allow for more risk, more innovation.
Yeah, to increase the error budget so they can actually launch things. It makes the cost of extreme reliability visible.
That's really clever. But it leads to that other counterintuitive idea. Don't overachieve your SLO. That feels wrong to an engineer.
It does feel wrong initially, but think about it. If your service is consistently running way bigger than its official SLO.
Users will start depending on that higher level.
Exactly. They build dependencies on performance you never actually promise them. It creates hidden fragility.
So what do? Intentionally make it worse.
Sometimes, yes. Google's Chubby Lock service team famously did this. If they hadn't had enough real outages to consume their error budget near the end of a period, they would actually schedule small, controlled outages. Synthesize downtime.
Seriously, they'd intentionally break things a little.
Yep. To force their users' other Google services to build in proper resilience, to handle failures gracefully, and to remind everyone what the actual contracted reliability level was. It manages expectations and prevents over-reliance.
That takes some serious discipline.
Okay, fascinating. Let's shift to the third pillar, eliminating toil. The quote you mentioned earlier is stark. If a human operator needs to touch your system during normal operations, you have a bug.
Yeah, it really sets the tone. And toil here has a very specific meaning in SRE. It's not just any unpleasant work. The definition is mundane, repetitive operational work providing no enduring value, which scales linearly with service growth.
Okay, let's break that down. Mundane, repetitive. Right. And it provides no enduring value. After you do it, the system is basically the same as before, and critically, it scales up linearly. If your service doubles, the amount of this work doubles.
Gotcha. So it's different from, say, admin tasks like meetings.
Yeah, that's overhead. Also different from grunge work like, say, refactoring confusing alert configurations. That might be messy, but it does create long-term value. It's an investment. Toil is not.
So what are the explicit hallmarks of toil? How do they spot it?
The book lists us a few key attributes. One, it's manual. Even if you're just running a script someone else wrote, your time clicking the button counts as manual work.
Okay.
Two, it's repetitive, doing the same thing over and over. If it's a novel problem, it's not toil.
Makes sense.
Three, it's automatable. A machine could do it, or maybe the system could be redesigned so the task isn't needed at all. If real human judgment is required each time, it's probably not toil.
Tactical versus strategic.
Four, exactly, it's tactical, reactive, interrupt-driven, like dealing with pager alerts as they come in.
No lasting impact.
Five, no enduring value. Like we said, the service state isn't fundamentally improved afterwards.
And the scaling part.
Six, it scales ON with service growth, linear scaling. More users, more traffic, more toil. Ideally, your operational load should scale sublinearly. You should get more efficient as you grow.
Okay, that's a clear definition. It sounds like reducing toil is a massive focus for SRE. Why is it so important?
It's fundamental to the SRE model. Google SRE has a hard target. Keep toil below 50% of every SRE's time, preferably lower.
50%, wow.
Yeah. At least half their time should be spent on actual engineering project work. Work that reduces future toil, adds features, improves automation, scales the system.
So they're hired as engineers, not just operators.
Exactly. That engineering focus is what allows SRE teams to manage more services, bigger services, without just hiring linearly more people. It enables that sublinear scaling. And it's a promise to hires. They join SRE because it's not a traditional ops role where you just fight fires all day. The target, I think it says they average around 33% toil across Google SRE. But yeah, the goal is max 50%.
So if toil is under 50%, what's the other 50% plus SA? What counts as that valuable engineering work for an SRE?
It's work that's generally novel, requires judgment, creates a lasting improvement. It's strategic, often creative or design-oriented. Things like Writing automation tools, developing frameworks, actually coding reliability or scalability features into the service, improving the monitoring system, tuning load balancing, writing good documentation, even consulting with dev teams on designing more reliable systems in the first place. It's proactive improvement.
Okay, so it's about building things to make the system better or easier to run.
Yeah.
But is toil always bad? I mean, sometimes doing a simple known task can be, I don't know, kind of satisfying, a quick win.
That's a fair point. Small amounts might not be terrible. Maybe it feels productive. Some people might even, find comfort in routine tasks sometimes. But the key is too much toil. That's where it becomes toxic.
Why-
Well, for the individual SRE, it means career stagnation. No time for projects means no promotions, no skill growth. It leads to burnout, boredom, feeling like a cog in a machine. And for the organization, it causes confusion about what SRE even is. It slows everything down. It can create bad incentives, like dev teams just throwing operational work over the wall to SRE. It leads to good people leaving. And it breaks that promise made to new hires.
So manage it aggressively, keep it under that 50% threshold.
Absolutely. Which leads right back to that SRE motto they mentioned. Let's invent more and toil less.
Right. Okay, so we've covered a lot. These three big ideas from Google SRE: strategically embracing risk, using SLOs and error budgets for clarity and control, and that relentless drive to eliminate toil.
Yeah, and it's important to see how they connect. They're not just separate tricks, they form a whole philosophy, really. It's about fundamentally rethinking that balance between keeping things stable and making things better, faster, and making sure engineers spend their time on work that has, real lasting impact. It's a model for making operations sustainable as you scale.
Definitely feels like these principles could apply well beyond just Google or massive tech companies. It makes you think differently about efficiency, risk, and where you spend your effort. So maybe a final thought for everyone listening. Think about your own world, your work, maybe even personal projects. Are there areas where you're striving for some kind of unattainable 100% perfection or reliability? And what if? What if good enough was actually better? What new things could you build? Or how much of your own toil could you eliminate if you defined an acceptable level of risk and focused your energy there? Something to chew on.
Welcome, curious minds, to another deep dive. Today, we're plunging into something that pretty much underpins every digital service you use. Your apps, search engines, everything. It's all about how these, massive systems tell us when they're struggling or maybe about to fail, and crucially, how we get machines to manage themselves. We've got some really fascinating material today from the experts at Google SRE, that's Site Reliability Engineering. It gives us a proper inside look at their principles for building really robust systems. We're focusing on their thinking around monitoring distributed systems and also the evolution of automation.
Yeah, it was really interesting here is how these two things, monitoring and automation, they're almost two sides of the same coin.
Yeah.
Especially for system reliability. So our mission today is basically to unpack Google's philosophy here, understand their definitions, look at the practical lessons they've learned from running things at just immense scale. You'll definitely walk away with a shortcut to understanding why your favorite online services stay up, mostly even when things go wrong behind the scenes.
Okay, let's dive into this then. Imagine a huge, incredibly complex machine. How do you actually know if it's just humming along nicely or if it's struggling? Or, worse, about to completely sputter out?
And that's exactly where monitoring comes in. It's indispensable.
So first things first, let's get our heads around some core terms. When we say monitoring, what exactly are we talking about here?
Well, at its heart, monitoring is really about collecting, processing, aggregating, and then, displaying real-time quantitative data. Think query counts, error types, maybe processing times, even how long servers have been running. It's basically the system's heartbeat, giving you that summary view, often, on a dashboard.
Okay. And the sources mentioned two main approaches within that, white box and black box monitoring. Can you clarify that distinction for us?
Absolutely. So white box monitoring. Think of it like looking under the hood of a car.
Bro.
It's based on metrics exposed by the system's internals logs, internal stats, interfaces, that kind of thing. Black box, on the other hand, well, that tests the external behavior, how a user would actually experience it. It's more about asking, is the system actually working correctly right now from the outside?
Right. And here's where it gets really interesting for me. Why monitor in the first place? I mean, beyond just seeing pretty graphs, what are the really crucial reasons?
Oh, the reasons are varied and, honestly, vital. You need it for analyzing long-term trends, like, say, database growth. Is it going to fill up? For comparing performance over time. Is our site slower than last week? That's a big one. And, crucially, alerting. This is when something is broken and needs fixing now, or maybe it's about to break soon. Monitoring also feeds into building those dashboards we mentioned, and it's just essential for ad hoc retrospective analysis, debugging when things go wrong.
Okay, so focusing on those crucial alerts. The sources really hammer home that paging a human interrupting someone is incredibly expensive.
Yeah, this raises a really important question. What's actually worth interrupting a human for? Google SRE has a very strong philosophy on this. Basically, an alert should never fire just because something seems a bit weird. Pages interrupt work, they interrupt personal time. Too many pages, what they call alert spam, it just leads to people ignoring them or second-guessing them. And that's dangerous because you might miss the real problems. The goal has to be good signal, very low noise.
And this leads us directly to another really important distinction they make. Symptoms versus causes.
Precisely. Your monitoring system, ideally, should help answer two key questions. What's broken? That's the symptom. And why? That's the cause. So, for example, serving HTTP 500 errors, that's a clear symptom, the cause. Oh, it might be that your database servers are refusing connections way down the stack. Or, slow responses, that's a symptom. Could be caused by overloaded CPUs.
I see. So white box helps you maybe detect those imminent problems that causes brewing internally, while black box confirms the active user visible issues, the symptoms.
Exactly. And it sounds like, depending on where you sit in the system, one person's symptom could easily be another person's cause.
Right. Okay, let's shift gears slightly. If you could only measure 4 metrics in a user-facing system, what would they be? This deep dive gives us Google's answer. The 4 golden signals.
Ah, yes. This is a real cornerstone, foundational stuff. The 4 signals are latency, traffic, errors, and saturation. So latency is just the time it takes to service a request. And it's really critical here to distinguish between successful requests and failed requests. Why?
Because a fast error is still an error.
Exactly. A fast error doesn't help the user.
Yeah.
So you need latency for both. Then traffic. This measures the demand on your system. For a web service, that might be HTTP requests per second, something like that. Errors is pretty straightforward, the rate of failed requests. These could be explicit failures like HTTP 500s.
Or implicit. What does that mean?
Implicit means maybe you get the right status code back, like a 200 OK, but the content is wrong or incomplete. That's still an error for the user. And finally, saturation. This tells you how full your service is. It really emphasizes the most constrained resources, CPU, memory, network bandwidth, whatever is closest to its limit. Often, latency increases are a leading indicator of saturation. And what's fascinating here is they also track predictions like, warning, your database will fill its hard drive in 4 hours.
Wow, predictive alerting. Okay, so if you monitor these 4, you're in pretty good shape, reasonably covered, but the material also talks about worrying about your tail. What's that all about?
Yeah, it's about not just looking at averages like the mean response time. Let's say your average latency is, 100 milliseconds. Sounds great, right?
Seems pretty good.
But maybe 1% of your requests, the tail, are actually taking 5 seconds. That's a terrible experience for those users. And if a user interaction depends on, say, 10 different backend services, that 99th percentile slowness of just one backend can easily become the median response time for the overall request. It cascades.
I see. The outliers really matter then.
Hugely. So instead of just averages, you need to collect request counts bucketed by latency ranges, often using exponentially distributed boundaries. That gives you a much better picture of that tail of slow requests.
That seems like a really practical tip. So how granular should these measurements be then? Do we need nanosecond precision everywhere?
Well, different things need different granularity, right? A CPU load probably needs higher resolution than, say, hard drive fullness. But collecting measurements very frequently can get really expensive resource-wise. Google suggests strategies like internal sampling combined with external aggregation. So, for example, maybe you record CPU usage every second inside the system, but then you aggregate those values every minute into buckets for storage and alerting.
Ah, okay. So you get the detail without drowning in data or cost.
Exactly. It's a balance. High-resolution where it counts, but efficient overall.
It really sounds like monitoring can become incredibly complex very quickly. What's the guiding principle to stop it spiraling out of control?
Keep it as simple as possible, no simpler. That's the mantra. Like any piece of software, your monitoring system itself can become fragile if it gets too complicated. Rules that reliably catch real incidents. They should be simple, dependable. And data collection or alerts that you find you're rarely using. They should probably be removed. Be ruthless. The goal is to keep monitoring distinct and loosely coupled from other things like profiling or deep debugging tools.
So what does this all mean for building new alerts? The source gives a brilliant set of questions to ask yourself first.
Yeah, and if we connect this back, these questions perfectly reflect that core Google philosophy on pages and pagers we talked about. First, does this rule detect an urgent, actionable, and actively or imminently user-visible condition that isn't already being detected?
Okay, urgent, actionable, user visible, and undetected. Got it.
Second, will you ever be able to ignore this alert, knowing it's benign? If yes, how can you stop that happening? Avoid false positives. Third, does it definitely indicate negative user impact, not just something internally weird?
Right, user impact is key.
Fourth,
That's
can
fair.
you actually take action in response, and is that action urgent? And finally, are other people already getting paged for the same underlying issue? Avoid duplication.
Essentially, it boils down to every time that pager goes off, you should react with urgency. The page must be actionable. It needs human intelligence, not just a robot following steps, and it should be about a novel problem.
Exactly. That makes perfect sense for keeping the system healthy and, just as importantly, preventing your engineers from burning out.
Now, the deep dive really stresses that monitoring decisions need long-term goals in mind. Sometimes, maybe taking a short-term hit to availability or performance can actually lead to greater long-term stability. Let's unpack a couple of examples they give. First up, the story of the Bigtable SRE team and their battle with over-alerting. What was going on there?
Right. So their SLO, their service level objective, basically their performance promises is based on the mean performance. But they had this large tail issue we discussed. Lots of very slow requests, relatively speaking. And this was just consuming an unacceptable amount of engineering time because the email and paging alerts were firing constantly, voluminously. They were spending way too much time just triaging alerts to find the few that actually needed action, and often they were missing real user problems in the noise. Plus, many pages just weren't urgent.
So, faced with this constant firefighting, what was the strategic trade-off they made? It sounds a bit counterintuitive.
It does. To fix it, they actually temporarily dialed back their SLO target. They lowered the bar to the 75th percentile performance, and they completely disabled the email alerts.
Wow, they intentionally lower their target.
Yes, temporarily. This gave them enough breathing room to actually focus on and fix the deeper, longer-term problems in the Bigtable infrastructure itself. Instead of constantly battling these tactical fires, the on-call engineers could do real engineering work.
Yeah.
So ultimately, backing off on the alerts actually led to faster progress toward a better, more reliable service in the long run.
That's a really powerful lesson. Strategic retreat for long-term gain. Okay, and then there's the story from the early days of Gmail.
Yeah, back then, Gmail was built on a system where individual tasks could frequently get descheduled, basically paused or stopped unexpectedly. With thousands and thousands of tasks running, this just led to an unmaintainable flood of alerts. It was chaos. So the Gmail SRE team built a tool, a clever little thing to kind of poke the scheduler to minimize the user impact when this happened, a workaround. But this immediately raised a really important question. Should they fully automate this workaround, or would doing that just delay tackling the real underlying scheduler problem?
That tension between the quick fix, the hack, and the proper long-term solution. That sounds incredibly familiar. I bet lots of teams face that.
Oh, absolutely. It's a classic technical debt dilemma. The source points out that pages requiring rote, algorithmic responses pages a machine could handle are a huge red flag. If a team is unwilling to automate those kinds of pages, it often suggests, maybe subconsciously, a lack of confidence or perhaps organizational will to address their underlying technical debt. And this is where managers and tech leads have a crucial role. They need to prioritize these sometimes time-consuming long-term fixes, even when the immediate pain of the paging might seem to subside because of a workaround. This is what Google calls thinking about the long run, not just dealing with each page in isolation, but considering the overall health and long-term future of the system and the team supporting it.
Okay, so let's move from monitoring knowing what's happening to automation, which is about doing something about it. This deep dive calls automation a force multiplier, not a panacea. What do they mean by that?
It means that automation, when you apply it carefully and thoughtfully, can massively amplify your capabilities. It lets you do more with less effort. But, and this is a big but, thoughtless automation or poorly implemented automation can easily create as many problems as it solves, sometimes more. The ultimate ideal, the goal, is what they call an autonomous system, one that requires neither manual operation nor external automation scripts. It just runs itself.
Right. So what are the key benefits automation brings when it is done well?
The most impactful ones, based on Google's experience, include, first, consistency. Humans, even the best ones, were just not as consistent as machines when doing the same task hundreds or thousands of times. Automation eliminates those small mistakes and oversights that creep in.
Yeah, human error is always a factor.
Always. Second, a platform. Good automation isn't just a one-off script. It provides a platform you can build on, extend, apply to more systems. And crucially, it centralizes fixing mistakes. You fix a bug once in the automation code, and it's fixed everywhere that code runs. Third, faster repairs. Automating responses to common faults dramatically reduces your mean time to repair, your MTTR. That frees up engineers for the really tricky novel problems.
Makes sense. Machines react faster.
Which leads to the fourth point, faster action. Humans just can't react as quickly as machines in many situations, especially in complex infrastructure. Automation is essential for critical things like failover, where milliseconds matter. And fifth, time saving. This can be hard to calculate upfront, but once a task is automated, anyone can potentially run it. It decouples the original expert operator from the operation itself.
I love this quote they included from Joseph Bironis, an SRE who led data center turn-up efforts. He said, "If we are engineering processes and solutions that are not automatable, we continue having to staff humans to maintain the system, feeding the machines with the blood, sweat, and tears of human beings."
Wow. Yeah, that really drives the point home, doesn't it? The human cost of not automating.
So, given that powerful image, why is Google so heavily biased towards automation? What makes it almost a default approach for them?
Well, fundamentally, it's their scale, planet-spanning scale.
Yeah.
They simply don't have the time or the people for manual machine handholding. It's just not feasible. Consistency, speed, reliability, these are paramount at that scale. And crucially, as we touched on, Google often builds its own APIs and infrastructure when commercial options don't cut it. This gives them complete control over their production environment, the whole stack, top to bottom. That level of control makes deep automation possible in a way it might not be elsewhere.
Okay, so what kinds of things do SRE teams typically automate at Google? What falls under their purview?
Oh, the range is huge. User account creation, cluster turn up and turn down, bringing entire clusters online or taking them offline, software rollouts, managing runtime configuration changes, many, many things. In Google SRE specifically, the primary focus tends to be on automating the lifecycle of systems creation, maintenance, deletion, rather than, say, managing the application data within those systems.
And the sources outline this really insightful model, a hierarchy of automation classes. It's like a path to fully autonomous systems. Can you walk us through that?
Yeah, think of it as levels of maturity in automation. Level 0 is no automation. Everything's manual. Think manual failover. Level 1 is externally maintained system-specific automation. This is like an SRE writing a specific script just for one task on one system. Maybe only they know how to run it.
Okay, the personal toolkit stage.
Exactly. Level 2 is generic automation. That script gets shared, maybe generalized a bit, used by more people or on more systems, a shared tool. Level 3 is internally maintained system-specific automation. This is a bigger step. The system itself starts shipping with its own automation. Like the database comes with its own built-in failover script.
Ah, so the automation becomes part of the product.
Precisely. And level 4, the ultimate goal is systems that don't need any automation. These are systems designed to be inherently self-managing. They notice problems, they automatically fail over or heal themselves without any human intervention or external scripts. SRE's goal is always to push things up this hierarchy, ideally creating systems that just don't need manual operations at all.
Let's make this more concrete with some real-world examples. First, that story about Google's ads database team basically automating themselves out of a job in a good way.
Right. So the ads database, originally on MySQL, they wanted to migrate onto Borg, Google's big cluster scheduler. Why? Well, benefits like eliminating manual machine maintenance, better resource use through bin packing, fitting more jobs onto fewer machines.
The Borg moves things around.
Exactly. Borg tasks can be moved frequently, rescheduled onto different machines, and that was just intolerable for database masters, which usually need stability. Manual failovers, when a master did need to move or fail, took 30 to 90 minutes. Way too long for their error budget, the acceptable downtime.
Okay, so that's the problem. Here's where the clever automation comes in. They created Decider. What did it do?
Decider was this automated failover daemon. Its whole job was to handle MySQL failovers, and it could do it incredibly fast, less than 30 seconds, 95% of the time. This is a huge philosophical shift. Instead of trying desperately to optimize for a lack of failure, which is hard with Borg.
They embraced failure.
Yes, they embraced failure and optimized for super quick recovery using automation. Now the cost, the trade-off, was that applications using the database needed to have more robust failure handling logic built into them. They had to expect brief interruptions, but the benefits were enormous. Mundane operational tasks dropped by 95%. Single database outages, no longer page to human. And they freed up 60% of their hardware resources because they could run more efficiently on Borg. They literally automated themselves out of the manual failover job, freeing them up for other more valuable work. It's a fantastic example of building an automated platform.
That's incredible. Okay, another fascinating case study. How Google applied automation to cluster turnups, getting a new cluster ready.
Right. Initially, turning up a new cluster was this incredibly complex, largely manual process. It was so involved, they often used it for training new hires.
Wow, trial by fire.
Pretty much. It involved hundreds of different component subsystems. Any misconfiguration, any small mistake was basically an outage waiting to happen later. There's that really striking, almost scary anecdote where some early automation misinterpreted a disk configuration setting. It assumed no storage was needed,
Oh, no.
and it wiped a multi-petabyte big table cluster. Just gone.
Ouch! That underscores the need for caution with automation.
Extreme care.
Eh.
Sanity checks, safeguards, absolutely critical.
So faced with all these inconsistencies and the potential for catastrophic errors, what was the ingenious solution they came up with?
They developed something called ProdTest. This is brilliant. They basically extended the standard Python unit test framework.
Like for testing code.
Exactly. But they extended it to allow unit testing of real-world services running in a cluster. ProdTest would go out and validate that a team's services were configured correctly in a new cluster. It would identify failures, give really detailed error messages, and the key thing was the feedback loop. If a turnup was delayed because of a misconfiguration found by ProdTest, a bug would be filed against the service team to extend their ProdTest to catch that specific issue in the future.
Ah, so it forced continuous improvement of the tests.
Precisely. And project managers could finally get reliable estimates for when a cluster would actually go live. It brought predictability.
Okay, so ProdTest finds the problems. Then this evolved into resolving inconsistencies idempotently. What was that about?
The next logical step, they paired each test and ProdTest with a corresponding fix. And these fixes were written to be idempotent. That means you could run the fix multiple times and it wouldn't cause any further damage. If it was already fixed, running it again did nothing.
Why is idempotency so important?
Crucial for automation. You don't want automation accidentally breaking things by applying a fix twice. So the idea was, ProdTest finds a problem, the associated idempotent fix automatically runs and corrects it. Simple, right?
Sounds good in theory.
Well, it had its own flaws. Sometimes tests were flaky, they'd fail intermittently for no good reason, and occasionally fixes weren't perfectly idempotent. This could sometimes leave the system in an even more confusing, inconsistent state.
And then this inclination to specialize, as the source calls it, created new problems down the line.
Exactly. To try and speed up turnups even more, they created a single, specialized turnup team whose only job was running this ProdTest and fix automation. And initially, it sped things up because it got really good at running the process. But over time, the real world kept changing rapidly. Google sees maybe 1,000+ production changes a day. The central turnup team's automation started becoming less relevant, less competent, because they weren't the domain experts for all the hundreds of services they were trying to configure.
They were disconnected from the service owners.
Right, and it created these weird organizational incentives. The teams who actually owned the services had less incentive to design them to be easily automatable by this separate turnup team. The feedback loop got weaker.
So after all that evolution manual, ProdTest, idempotent fixes, central team, where did Google land with cluster turnups? What's the current state?
Well, a crucial security mandate actually provided an escape route from that central team model. They had to replace the older, less secure SSH-based automation. They moved to using admin servers. These are internally built systems driven by strict access control lists, ACLs for permissions, and using RPC's remote procedure calls for communication. Much more secure, auditable, fine-grained control. This shift led to what they call a service-oriented cluster turnup. Now, the service owners themselves are responsible for creating these admin servers with well-defined APIs for the turnup and turndown actions specific to their service.
Putting the responsibility back with the experts.
Exactly. So now they have a process that's low latency, confident because the experts own it, accurate, and it scales much better with that constant rate of change across Google's infrastructure.
This whole journey of automating infrastructure really seems to culminate in something like Borg, which you described earlier as the birth of the warehouse-scale computer.
Yeah, Borg really represents that shift away from thinking about individual machines Instead of static assignments, this machine runs that job board, treats a whole collection of machines, thousands of them, as just a managed sea of resources, a giant pool. The core idea was to turn cluster management itself into something you control via API calls to a central coordinator, like programming the entire data center. And this just unlocked huge gains in efficiency, flexibility, and crucially, reliability.
So what could they do with Borg that they couldn't easily do before? What did it enable?
Well, for example, it enabled continuous automatic operating system upgrades across the fleet with a minimal ongoing effort, no matter how huge the production deployment got. Small deviations in a machine state, Borg automatically notices and fixes them. Thousands of machines can literally be born, die, go into repair, come back online every single day with virtually no SRE effort needed to manage that churn. As Ben Trainersloss, a key SRE leader, noted, by treating cluster management as a software problem, Google achieved an autonomous system, not just an automated one. It strongly suggests that once you reach a certain scale, your systems must become self-healing, self-repairing. There's no other way.
It really sounds like automation is fundamentally about achieving reliability, which, as you said, this deep dive calls the fundamental feature. But is there a potential downside? Can you have too much automation?
That's a really important and maybe slightly philosophical question the material raises. There's this fascinating analogy they draw with non-computer domains, like airplane cockpits. When automation becomes highly effective, really good, the human operators, the pilots, or in our case, the SREs, they can gradually lose direct contact, lose their intuitive feel for the system. Then, when the automation inevitably fails, and it will fail sometimes, no automation is perfect. The humans might actually be unable to take over and operate the system successfully.
Because their skills have faded.
Exactly. Their skills might have atrophied. Their mental model of how the system actually works might be out of date because the automation was hiding the complexity. In some cases, manual actions might not even be possible anymore if the system evolved around the automation.
And we even saw that chilling example title, Automation, Enabling Failure at Scale. What happened there?
Yeah, that's a critical anecdote they share. It details how an automation tool, during a decommissioning process, misinterpreted an empty set of machines it was supposed to erase. Instead of erasing nothing, it interpreted empty set as erase everything.
Oh, goodness.
And it led to the accidental wiping of disks on almost all the machines in Google's global content delivery network worldwide. It forced them into days of painstaking work reinstalling machines. And of course, it led to adding extensive sanity checks, rate limiting, and other safeguards to their automation tools. It's just a really powerful, sobering reminder that even beneficial automation, if not meticulously designed with safeguards, can have absolutely catastrophic consequences, amplified by scale.
So, pulling all this together, the power, the pitfalls, the evolution, what's the core takeaway for you, the listener, whether you're at Google scale or managing just a few servers?
I think the first thing is, don't wait until you are Google scale to start thinking about and implementing automation. It provides huge benefits beyond just time saving, that consistency, the platform capabilities, the faster repairs. Those matter at almost any scale. And critically, the highest leverage point for building reliable, automatable systems is right at the beginning, in the design phase. Just bolting on features rapidly might feel productive in the short term, but it rarely makes for a truly resilient system later on. Autonomous operation is incredibly hard to retrofit. Instead, the focus should always be on standard, good software engineering practices from day one. Build decoupled subsystems, define clear APIs between them, minimize side effects. That makes automation possible.
So the big picture here seems to be that reliability isn't just about preventing problems from happening.
No, because problems will happen.
Right. It's more about designing systems and, importantly, the team supporting them to inherently learn, adapt, and even autonomously recover from those inevitable failures. So thinking about everything we've covered, what insights really stand out to YU from today's deep dive? Maybe it's the true cost, the human cost of that pager going off unnecessarily, or the sort of counterintuitive wisdom of embracing failure to enable rapid recovery through automation, or just that constant tension between the quick fix and long-term stability. Whatever it is, we really hope this guide has given you some fresh perspectives, maybe some actionable ideas.
Yeah, and maybe the next time you use an online service and it just works perfectly, take a second. Consider those hidden layers of monitoring, keeping it alive. Think about those 4 golden signals being constantly watched. And the intelligent automation that, in many cases, is quietly fixing problems before a human even gets notified. It definitely leaves us with an important question to ponder. How can you apply these principles as simple as possible, no simpler? Designing for testability, designing for automation. How can you apply those to a system in your own life or your own work?
Great question to end on. Until next time, keep that curiosity well fed.